Okay, in this video we're going to start introducing the notion of a vector field. So just kind of as a build up for where we've been and where we're going, recall that in Calculus 1 and 2 we're generally dealing with functions of one variable. So the domain is just the real numbers, and the range, or sometimes called the codomain, is also just the real numbers. So we have functions of the form like y equals f of x, and that's it. And then in the first half of Calculus 3, we have vector valued functions. So in other words, we've got one variable in the domain, so I've written that as r, so just one real number goes into the domain, and then a vector comes out in the codomain. So we graphed vector valued curves, vector valued lines. Sometimes those were written with parametric equations and sometimes with vector equations. Then we moved on to multivariable functions, but they are scalar valued multivariable functions. So they have n inputs, and generally we dealt with n equals 2 or 3, and then they had a single output. So remember, we had partial derivatives, we had multiple integrals, and so on and so forth. And generally here we wrote things like z equals f of xy, or maybe like w equals f of xyz. Okay, so now we want to generalize this by putting these two ideas together. And so the most general way to do that, which is something we won't do, will be we have a function whose domain takes n inputs in. In other words, it's an n vector, and its codomain, or its range, gives us an m vector. So you deal with this kind of thing in linear algebra. It'll be like an m by n matrix, but this is not something that we'll deal with in this course, although you can generalize it quite easily to this. What we will deal with is something that's called a vector field, and the definition is pretty simple. So a vector field in Rn, it's a function from Rn to Rn. So we're going to keep the domain and the codomain having the same number of entries. So generally we think about the domain as having n variables, and then the output will be a vector that is n in length. Okay, great. And then one special type of vector field is called a gradient vector field. So sometimes this is called a conservative vector field because it represents some important properties in physics. So a gradient or conservative vector field is a vector field that can be defined by taking the gradient of an n-variable function. So in other words, f, capital F, I should say, is the gradient of little f, and little f is a multivariable scalar valued function. And so that function f is called the potential function. Okay, so before we do some examples, I want to give you some standard notation for vector fields. And standard notation for vector fields in R2 is as follows. So generally we'll write f of xy, and so this will be the vector field built by p of xy, q of xy, or maybe p of xy in the I direction plus q of xy in the j direction. It's pretty common to see them in both ways. And then, if you have a vector field in R3, so that means you need three inputs, x, y, and z, and that means you'll also have three outputs, and we'll call those p of xyz, q of xyz, and r of xyz. So that's the standard notation for a vector field in R3, and usually we'll write P in the I direction, Q in the J direction, and R in the K direction. Something like that. Okay, so now I want to look at some graphical representations of vector fields, and we'll start with a pretty simple one. So the first one that we'll look at is f of xy equals the vector field xy. So notice that this thing can also be written as x in the I direction plus y in the j direction. Okay, so you might think, well, how can we look at a graphical representation of this? Because essentially we have 4 dimensions. We have 2 domain dimensions and 2 range dimensions, but we can do it in the following way. So we'll draw the XY plane like this, and then at selected points in the XY plane, we will draw a vector which is given by the output of this vector field at that point. So for example, if we go here to 1, 1, we'll go up here. Now we want to plug 1, 1 into this vector field. Notice that's also going to give us 1, 1. And then what we'll do is we'll draw the vector 1, 1 at this point. So we'll get something like that. And then what we'll do is do that at every point. So let's go ahead and draw down here, which is like 1, negative 1. So that'll give us that vector. And then negative 1, 1. So that'll give us that vector. And then finally negative 1, 1. So that will give us this vector pointing up this way. Okay, good. Now let's look at some other ones. So notice along the x-axis, we'll just have a vector pointing straight along the x-axis to the right or to the left, depending on if we're in positive or negative values of x. Here we'll have vectors pointing up or down. Okay, great. And then notice maybe here at 1, 1/2, we're going to be pointing in that direction. Good. And notice that all of these vectors lie on lines radially emanating from the origin. So we'd have another one right here pointing up that way. Okay, great. So you can think of this as like some sort of explosion going out. We have a radial picture of vectors emanating from the origin, and notice down here is the only time you get 0 vector for the vector field. Okay, great. So I'll clean up the board and then we'll look at a couple more graphical examples. So the next one I want to look at is this one right here, which is f of xy equals negative yx. So let's get a picture of this going. Okay, so I'm going to go ahead and put a couple of points here. Let's put points along the x-axis like that and the y-axis. Okay, so notice here at the point 1, 0, if we plug 1 in for x and 0 in for y, we will get the vector 0, 1. So that thing is pointing up here like this. Okay, good. Now, let's notice back here at 1/2, if we plug 1/2 0 in, we get the vector 0, 1/2. So we'll get about half of that. And then if we plug in 1/4, we'll get 1/4 of that, and so on and so forth. Okay, now if we plug 2 into this, we'll get twice that vector. Okay, great. Now notice if we plug in the point 0, 1, we will get the vector negative 1, 0. So that's going to be the vector pointing this way. Okay, good. Then if we plug in the point 0, half, we'll get this vector pointing back in this direction. So we'll get negative 1/2, 0, that vector. Good. And then notice right here, we'll get a vector pointing back 2 units. Okay, now let's look right here. So this is the point negative 1, 0. So if we plug negative 1, 0 into this, we will get 0, negative 1. So that's going to point down. And then if we do half, it's going to be like that. And then if we do 2, it's going to be a little bit longer. Okay, great. And then let's try this one. So if we plug 0, negative 1 in, notice we're going to get the vector 1, 0. So that's going to point in that direction. If we do 1/2, we'll get kind of the same thing. And if we do 2, we'll get the same thing but longer. Okay, so that's what our vector field looks like along the coordinate axes. Now let's look at some other points. So let's maybe go up here and look at this point 1, 1. So if we look at this point 1, 1, we will get the vector negative 1, 1. So notice the vector negative 1, 1 is pointing back in this direction. Okay, good. Now let's go ahead and look at the point, let's see what this is, -1, 1. So if we look at the point -1, 1, that's going to turn into the vector -1, 1. So that's going to take us down like that. Okay, good. And then similarly, this guy is going to take us down like this, and this guy is going to take us like that. Okay, great. And now we can also kind of fill in those spots. Good. So as you can see, we kind of get a spiral in this case. So the vector field is pointing around in a circle. Okay, great. So I'll clean up the board and then we're going to look at one more graphical example. Okay, for our last graphical example, it looks pretty similar to the last one, but I've erased the minus sign. So I have yx. So let's go ahead and draw our picture here. So let's see, we have our xy plane. I'm going to put 1 and 2 on both of the axes just for us to work with. And now let's see what we get along the coordinate axes. So notice over here, this is the point 1, 0. So that's going to turn into the vector 0, 1. So in other words, that's going to be pointing up like that. Okay, good. Now let's go over here and notice this is the point 0, 1, and that's going to turn into the vector 1, 0, so that's going to be pointing that way. Okay, and if we go down here to a half, we'll get the same thing, but these are just 1/2 units. So those point towards each other. Great, and then if we do 2, we'll get the same thing, but those are pointing towards each other like that. So we get something like this. Okay, great. Now let's see what's happening at 1, 1. So notice 1, 1 is going to be pointing in that direction because all we do is switch the order of x and y, but switching the order of 1, 1 just gives us 1, 1. And similarly, if we do 2, 2, it's going to go like that. If we do half, half, it's going to go like that. Okay, great. Now, by some symmetry, we have the same thing going on down here. So I'll let you guys fill that in, but notice over here in the third quadrant, x and y are both negative, so you get this same kind of picture. It's just pointing in the opposite direction. So we get something like that, and then along this line, we'll be pointing away like this. Okay, great. Now, the next thing to notice is maybe what's happening over here, like at the point 1, -1. So at the point 1, -1, that's going to switch to the point -1, 1, and so that's going to be pushing back towards the origin. So we can draw that like this. Okay, great. And then similarly, here at the point -1, 1, that's going to turn into the vector 1, -1, and that's going to be pointing back at the origin as well. Good. So we've got something like that going on. And this pointing back towards the origin will happen at every point along this diagonal line. Okay, so now I think we have a pretty good feel for what's going on. I'm going to draw in something called a flow line with a different color. Okay, so let's notice that if you are in this region, the vector field will push you in this direction towards this asymptote. So we have a general flow like that. Okay, good. And now if you're up here in this bit, we'll have a general flow in this direction. If you're over here between these two diagonal lines, we'll have a general flow in this direction. And similarly down here, we'll have a general flow in this direction. Okay, great. So I'll clean up the board and then we're going to do some calculation type examples. For our first example, I want to find the gradient vector field with this potential function. So we have f of x, y, z equals xy plus sine of y, sine of z. So from previously in the course, we used the gradient of a function in order to find directional derivatives. And we've also taken lots of partial derivatives, so this shouldn't be too bad. So we need to take the gradient of f, but let's just recall that that's the partial with respect to x, the partial with respect to y, and the partial with respect to z. So let's see what we get for that. The partial of this function with respect to x is obviously y, because that second part of the sum is a constant with respect to x. The partial with respect to y will give us x plus cosine of y, sine of z. So over in that second part, the sine of y is the only variable part, and sine of z is a constant with respect to y. And then finally, for this third component, we're going to get sine of y times cosine of z. Okay, so there's our gradient vector field for this potential function. Okay, I'm going to clean up the board, and then we'll talk about how to find a potential function. Okay, for this next example, we're going to find a potential function. So the vector field that we want to work with is this one given by 2x cubed y to the fourth plus x, and then 2x to the fourth y cubed plus y. So we'll see that this is a conservative vector field. Otherwise, it would be impossible to find a potential function. Okay, so what we need is we need some function f, which will be a function of x and y, that satisfies this rule. So we need the gradient of f to be capital F, that vector field. In other words, the gradient of f is given by the partial with respect to x and the partial with respect to y. So we have two equations to solve. We need to solve the partial with respect to x is got to be equal to this first component. So that's going to be 2x cubed y to the fourth plus x. And the partial with respect to y needs to be equal to this second component. So that's 2x to the fourth y cubed plus y. Okay, so now what we want to do is take the antiderivative of this with respect to x. So I'll write that in the following way. So antiderivative with respect to x, so that's going to give us the following. So notice that will give us 1/2 x to the fourth y to the fourth plus xy. So let's talk through this part. So notice we're going to increase this exponent by 1, divide by the new exponent. 2 divided by 4 is obviously 1/2, and then 1/2 x squared. Okay, so let's talk through this. So we raise the exponent by 1, that's going to be a 4. We divide by that new exponent. 2 divided by 4 is 1/2. And then the antiderivative of x is obviously 1/2 x squared, but I'm missing one thing. I'm missing my constant. But if I'm taking a constant with respect to an x integral, that can actually be a function of y. So I'll just write that as g of y. Okay, so now what I want to do is take the partial of this with respect to y. So notice this is playing the role of f in this case. So if we take the partial of this with respect to y, that should match with that guy up there. So let's see what we get when we take the partial of this with respect to y. So notice that's going to give us 2x to the fourth y cubed for this first term. That's going to give us 0 for this second term, because that's just a function of x. And then that's going to give us g prime of y for our third term. Okay? So now this should be equal to f sub y. Now what we do is we compare these two. And notice comparing these two, we've got this term and this term, which are the same, and then we've got one term left over, which in the bottom equation is g prime of y, and the top equation is y. So what that tells us is that g prime of y needs to be equal to y. In other words, g of y is equal to 1/2 y squared plus a constant. And this is an actual constant, not a constant with respect to x or anything like that. Okay, so now what we can do is we can put this value of g into this function, and that will give us our potential function. So we have 1/2 x to the fourth y to the fourth plus 1/2 x squared plus 1/2 y squared plus a constant. And that is the final answer. Okay, we'll do one more example. Okay, for our final example, we want to show that there is no potential function for this vector field f given by x squared minus xy and y squared minus xy in each component. So let's do this by trying to find a potential function and then failing. So we want to find a function so that when we take its gradient, we get f. So in other words, the partial with respect to x needs to be the first component, and the partial with respect to y needs to be that second component. So what this is going to tell us is that the partial with respect to x is x squared minus xy, and the partial with respect to y is y squared minus xy. Now we're going to play the same game that we did in the previous example. So I'm going to go ahead and take the antiderivative with respect to x on this side. So notice that's going to give me f equals 1/3 x cubed plus 1/2 x squared y plus g of y. So my constant of integration here is a function of y. Great. Now I'm going to take the partial derivative of this with respect to y. So that's going to create f sub y equals, so that's going to give me 0. That's going to give me 1/2 x squared, and then that's going to give me g prime of y. So plus g prime of y. Okay, great. But now let's compare both sides of this equation. So comparing both sides of this equation, that tells us that 1/2 x squared plus g prime of y equals y squared minus xy. But now we can move some things around. Notice that's going to give us g prime of y equals y squared minus xy minus 1/2 x squared. But this is a problem because on the left-hand side of the equation, there are only y's. But then on the right-hand side of the equation, there are x's and y's, which is impossible. And so no such g exists, but if no such g exists, then no such f exists, but that means there is no potential function for this vector field. Okay, this is a good place to stop this video.